All right, this is Jack Jackson, and we're back at our look at quadrilaterals. We took a little detour for a while talking about parallel lines and transversals to parallel lines, and we proved the Z property and C property and F property for transversals to parallel lines. And we're going to use those properties when we deal with quadrilaterals that have some parallel sides. That's trapezoids. So let's start with looking at trapezoids in this video. Now, our definition is a trapezoid is a quadrilateral with at least one pair of parallel sides. Last week, in the last playlist, we talked about why we wouldn't want to use that inclusive definition so that parallelograms, quadrilaterals with two pair of parallel sides, are also trapezoids. The pair of parallel sides are called bases. The pair of not necessarily parallel sides are called legs. The pair of angles whose intersection is a base are called a pair of base angles. The lines with endpoints at the midpoints of the legs is called the midline of the trapezoid. A line with endpoints on different bases, which is perpendicular to one base, is called an altitude of the trapezoid. And in Euclidean geometry, the common lengths of all altitudes is called the height of the trapezoid. Okay, so let's illustrate some of those on a drawing. So here's my classification and properties of quadrilaterals, big sketch, big activity in GeoGebra, and we can classify by number of parallel sides. And here is a trapezoid and different kinds of trapezoids. So this is a general trapezoid. The way this one is built, it cannot become, it gives you all trapezoids. You can degenerate it down to a line segment or to a triangle, but you can't make it non-simple the way I've got it constructed. Notice that the blue sides are always parallel. We have a tendency to use these little arrows sometimes to indicate parallel sides. So all of these things that you're looking at here are trapezoids in Euclidean geometry. So when you think of a trapezoid, don't necessarily just think of something, maybe you're thinking, okay, well, a trapezoid looks like that, for example. That's a possibility, but these sides don't have to be, they have to be parallel, but they don't have to be horizontal. Uh, you could have, if they are horizontal, you can have one of the sides with a positive slope and one with a negative slope. They could be congruent. They could be parallel somewhere in here. They might be parallel for the legs. They could be, one could have positive slope and the other one have positive slope as well. One could have positive slope and the other negative slope if we're assuming these are horizontal. So there's lots of different shapes that we could come up with for trapezoids. So when you're thinking of a trapezoid, it's useful to start thinking of the way you think of a trapezoid as this dynamic class of figures. Okay, so in every case though, these blue sides are parallel. Okay, and those two blue sides there, that is AB and DC, are the bases. Then the green and red sides, which may not be parallel, they may or may not be congruent, those sides are called the legs. Okay, we have uh, we have the two diagonals, as always. That makes two triangles. Notice that they're not necessarily congruent, like they were in a kite. Not necessarily congruent there. There's the interior. Um, let's see, what are some other things that we can draw? So if we draw a line segment perpendicular there and go from where that intersects here to there. Let me hide that guy. Okay, I don't need to label this point or this one either, really, for that matter. Okay, but if we take this and then let's go ahead and mark that angle so we see it's a right angle. Okay, and I think it's clear it's a right angle, so we don't need a label. Okay, so there's a right angle. This is an altitude. let's see, let's call it altitude, and let's give it its name and its value, both as a label, not its name and its value, sorry. I want its caption and value. So there's the altitude. The altitude is the segment. Its length is the height. Okay. So so there's an altitude, and there's the height of this, and it stays the same distance apart no matter where we are on there. That's not a property that we have in other geometries, but it does work in Euclidean geometry just fine. Okay. Let me go ahead and make a checkbox for that, and where we can hide and show the altitude. That's 09. So let me go ahead and just click all of those, go to settings, advanced, and say 09. Yeah, lowercase o, sub 9, I believe. That should hide or show them there. Okay. So we can see the altitude. These guys here are called bases. These guys are called legs. Let's see, what else do we have? Oh yeah, we have midline. Let's go ahead and do that. So we can make a midpoint. Where is the midpoint? Right in here. Midpoint here. And a midpoint here. Okay. Let's rename it. Midpoint, mid 1 and mid 2. Let's rename it. Whoops. So those are midpoints there. This guy we don't need. And then this is our midline here. And let's go ahead and label that. Whoops. Click up here. And let's label that as the midline. Okay. And let's go ahead and make a hide show box for that. And that is U9. And so we'll go and do this to do the hide show for that. Okay. So there's the midline. Okay. So interesting properties that the midline might have too, but there's the midline. Mid connects the midpoints of the legs. Altitude is perpendicular to the bases. Okay, so I think we, okay, base angles and bases. Okay, so let's talk about base angles next. Okay, so a pair of base angles would be these. So this angle here, here, and this one here. Okay, so let's say these two. Okay, notice they're not necessarily the same size. Okay, but that's a pair of base angles. And you also have another pair of base angles up here. Actually, you know what? I already have a thing that can show all the angles. All I have to do is click on this. So this one at A and B are base angles. The one at D and C are base angles. Okay. Now A and D are consecutive angles, but they're not a base pair. C and B are consecutive angles, but not a base pair. The A and B are a pair of base angles. D and C are a pair of base angles. Okay, so does that make sense what those are? Okay, now we have several subclasses of this. Okay, if it so happens that you get, we're getting close to it there, where you have a right angle right there. Okay, you would get a right trapezoid. Okay, so a special kind of trapezoid is a right trapezoid. It has, by definition, it's going to have one, at least one, right angle. Now, let's look back. Let's go back and see if there are any properties of trapezoids that you might have. Can you notice anything about the trapezoid angles? Well, one thing we have some things about parallel lines. Let's use them, right? We looked at all this thing about these two lines being parallel. What does that say about these two angles right there? Well, you have your C property, says that these alternate are interior angles on the same side of the transversal. So you're thinking about line, the whole line, AD uh, intersecting or cutting the two parallel lines, the whole line DC and the line AB. Well, these angles right here, those are of course those are the markers for the angles, but angle CDA and angle DAB, those are interior angles on the same side of the transversal. They got to be what? Supplementary. So if you add these two up, you're going to get pi, right? So 2.15 plus 0.99, that should add up to about 3.14, roughly pi. So these are be exactly supplementary, okay? And the same thing is true over here. So one of the properties that you have, really pretty much the only one besides the defining property that you have of parallel sides, is that you have a pair of consecutive non-base pairs that are supplementary. Okay, so uh, this is saying A and B are base pair of base angles, C and D are another pair of base angles. Quadrilateral is a trapezoid if and only if each consecutive pair of angles that are not a pair of base angles are supplementary. It turns out that the diagonals must intersect and it has a convex interior. Okay, that's also a property we have for trapezoids, but that's pretty much it. There's not a lot more. Now let's think about trapezoids in spherical geometry. Well, there are not any, right? Because there are no parallel lines in spherical geometry. Well, what about hyperbolic geometry? Well, in hyperbolic geometry, remember we have the C property in one direction. If we're going to get a pair of consecutive angles that are congruent or supplementary, excuse me, then you will get a pair of parallel sides. But you can get parallel sides without having consecutive angles, uh, non-base pair that are supplementary if you're in hyperbolic geometry. So let's go back to the notes here and just look real fast here. Here are some static examples of some trapezoids in hyperbolic geometry, right? So here we have some, here we have trapezoids. Because there's so many different possibilities for parallel sides uh, in hyperbolic geometries, where there's this class of trapezoids is extremely broad, no real special properties except for the defining property of a pair of parallel sides. In fact, this one here, this first one, the second one, and the third one are actually parallelograms, right? So if you look at, here's the side containing the line containing that side and the line containing the opposite side, those are parallel. They don't intersect. And the line containing A and B, that's this line, and the line containing C and D, that's this line. Those don't intersect, which is all the same plane. So those are parallel sides as well because they're lines containing are parallel. So that's a parallelogram. Both pair of opposite sides are parallel. Same way here, right? This one and then the one out here are parallel, and this one are parallel. Same way for this one. This is also a parallelogram. So it's a trapezoid, but it's more specific. This is a trapezoid. Now these sides, the purple sides here and here, are the legs because they're not parallel. If you take this line here from BC and the line AD, you see there is an intersection point over here. But these two vertical sides are parallel. So that's a trapezoid that's not a parallelogram. In this case, the blue ones here are the bases. I guess in all these cases, the two blue sides are the base, or the blue and the green one here. And you could think of the other ones. I guess I'm thinking of the two red ones as being the bases here. And of course, in a parallelogram, you can think of either set as the base and the other as the legs. It goes either way. Okay, but in a general trapezoid, you got a parallel sides that's the base, and the potentially non-parallel sides is the pair of legs. Okay, so not a lot we could say. There's a good picture of one there. What do they have here? We got all properties shared by all quadrilaterals because it is a quadrilateral. At least one pair of parallel sides. Each non-base pair of consecutive interior angles is a supplementary pair. It's a convex quadrilateral. And this one is something that you may not definitely have not seen from what we've done so far. Is it turns out the length of the midline is the average of the lengths of the legs in Euclidean trapezoids. That's going to require a little bit more proof. We'll come to that a bit down the road. And so here's equivalent conditions for a trapezoid. It's a trapezoid, has at least one pair of parallel sides, or you can say it's a quadrilateral with a pair of consecutive supplementary angles. Turns out in Euclidean geometry, those two things are the same. And in hyperbolic geometry, if it has a pair of consecutive supplementary angles, then it has to be a trapezoid. But if it's a trapezoid, it doesn't have to have a pair of consecutive supplementary angles because there's just so many parallels that are going on there. Okay, and there's the proof, which I've kind of already gone over, and there's that. So that is trapezoids. Let's continue to talk about right trapezoids. Okay, now let's think about it. In Euclidean geometry, if you got a right angle here, this other one has to be a right angle by the C property. So notice I didn't say a right trapezoid with I had to have two right angles. I said it's just had to have one, but of course when it says with A, that means at least one right angle. Let's go ahead and just say that specifically. At least one right interior angle is a right trapezoid. Okay? And of course, it turns out in Euclidean geometry either has exactly two right angles or they're all four right angles. There's no in Euclidean geometry, there's no way to get just one right angle on a right trapezoid or exactly three. It's got to be exactly two or exactly four. Because remember, on any trapezoid, these two have to be supplementary by the C property, as do these two. So if one of them's a right angle, if they're supplementary and one of them's right, well, the other one's right too. Okay. And so it has all the properties of a trapezoid, plus it has to have at least two right angles. Okay. Let's stop right there for this video.